am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. This is our third lecture for the Control System 1. In this video, we will discuss on the mathematical modeling of electrical systems. This video consists the mathematical modeling, necessity of mathematical modeling, the classification, input-output representation and transfer function model, the concepts of poles and zeros, and the mathematical modeling of electrical system. So what is mathematical modeling? Mathematical modeling is the art of translating problems from an application area to the tractable mathematical formulations, whose theoretical and numerical analysis provides the answers, insight and the guidance useful for the originating application. The mathematical modeling is indispensable in many applications. Now, a system in control engineering may be a liquid level system, a temperature control system, an accelerometer or any conveyor belt system. To study these systems, it is very useful to have the mathematical models of the system. So, a mathematical model consists of a collection of equations describing the behavior of the system. Now, there are many methods to obtain the system models. The dynamic behavior of the system is represented by a set of differential equations. Now, the process of developing a mathematical model, which is known as the mathematical modeling, a model may help to explain a system and to study the different differential equations which are actually represent the dynamic behavior of the systems. Now, mathematical models are usually composed of relationships and variables. The relationships can be described by operators such as the algebraic operators, functions, differential operators, etc. And variables are abstractions of system parameters of interest and that can be quantified. Now, these are the necessity for the mathematical modeling, because mathematical modeling of a system is the process of drawing the block diagram and finding out the differential equations to determine their performance and the transfer functions. So, next is the classification. So, after getting the set of differential equations which are obtained based on the fundamental laws of the physical systems. For an example, the motion of mechanical system can be represented by Newton's law of motion, and in that electrical system it can be represented by the KVL or KCL. So, in first approach of modeling, system can be classified as two types. One is input-output representation, which describes the relation between the input and output of the system. And another is the state model, which describes the relation between the input states and output of the system. Now, this input-output representation can be further divided into two types. One is differential equations relating to the input and output, and another is the transfer function representation. So, in this video, we will discuss on the input-output representation. Now, the differential equation model and the state model are referred to the time domain models, as these representations are given in terms of the functions of time, whereas the transfer function model is known as the frequency domain model. Now, the model of the system can also be obtained from the knowledge of practical input and output signals, and a known input signal is applied to the physical system and the corresponding output is measured. And in case of state variable model, actually the transfer function model gives the relationship between the input and output variables only. So it is not possible to find out the other variables. So if we consider the RLC circuit, then the voltage across inductance or current through the inductance in the circuit, that means the transfer function modeling is a terminal approach where we can find only the output but not the state of the other variables inside them. So this drawback can be eliminated using the state variable model, which we can find the state of the other variables of the system at a time. So first consider the input-output representation. So let us consider a series RLC circuit where the input voltage is Vi and these are the three variables, that is R, L and C. Actually these are the parameters and variables are voltage, the current, and if charge is present then Q. So voltage is, input voltage is VIT, output voltage is V0T, that is taken across the capacitance, and the drop across R is considered here VR, and drop across L is considered here VL, and drop across C is considered as VC. So to perform the mathematical modeling, first we need to find out the equations that describes the behavior of the system. So for the electrical system, the dynamic behavior of the system can be represented by the differential equations, which can be represented by the KVL here. So for this loop, we can consider the KVL, and for that one, if we consider the drop across R is R into IT, and drop across L is L di dt, and the drop across capacitance, that is 1 by C integration I dt. Then using KVL, we can say that this VI, that is equal to summation of the drop across this resistance, inductance and capacitance. So VIT equal to RIT plus DIDT plus 1 by C integration IDT. And the output is taken across the capacitance. So V0T is actually the VC and VC is the 1 by C integration IDT. So this is the input-output representation. So in input-output representation, we are getting the dynamic behavior of the system, which is represented by the set of differential equations. In case of electrical circuit, we can use the Kirchhoff's law, whereas if it is a mechanical system, then we can represent it by the Newton's law of motion. So this is the input-output representation. And next is the transfer function model. So a transfer function is the ratio of a system output to the input in the Laplace domain. And the main important thing is we are considering that all initial conditions are 0. So the transfer function of a system is the Laplace transform of its output by input at the 0 initial condition, or it is the Laplace transform of its impulse response under the 0 initial conditions. So for this system, we have already discussed how to get the input-output representation. Now we are converting it into the transfer function model. So for the same system, the voltage is applied and the current is flowing, that is IT, and the output is taken across the capacitance. So if we apply the KVL in this loop, then we are getting VIT equal to RIT plus LDIT dt plus 1 by C RDT. And output equation represents V0 to equal to VC equal to 1 by C integration IDT. Now we are taking the Laplace transform in the both sides, and transfer function of the actually transfer function is applicable for the linear time invariant systems. And we are considering the 0 initial conditions. So under this 0 initial condition, if we take the Laplace transform in the both sides, then we are getting V of Is equal to Ris plus Lsis plus 1 by Cs into Is, as well as V0s is equal to 1 by Cs. Now we know that transfer function is the ratio of the output divided by the input. So in this case, the output is the V0t. So the transfer function is the ratio of V0s by Vis under the zero initial condition. So when we are taking the ratio of V0s by Vis, it becomes 1 by Lc by S square plus R by Ls plus 1 by Lc. Now the denominator has the highest power is equal to 2. So this is a second order system. So from this way, we can say the order of the system is the highest power of the denominator. So this is the transfer function model. And to obtain the transfer function model, we have done the steps that we have written the mathematical model of the system based on the fundamental principles and the results in set of differential equations that relates the input and the output. And after that, we obtain the Laplace transform of the differential equations by assuming initial conditions are the 0. And finally, we have found out the ratio of Laplace transform of the output to the Laplace transform of input. Now, after getting the transfer function, we need to what is the poles and what are the zeros. So, generally a function can be represented in this polynomial form like this. F of s equal to f0 s to the power n plus f1 s to the power n minus 1, f2 s to the power n minus 2 plus f3 s to the power n minus 3 and so on. Now, the transfer function of the control system can be represented in the same manner, and Gs equal to Cs by Rs, where C is the output of the system and R is the input of the system. So, Cs is the Laplace output in Laplace domain and Rs is the input in Laplace domain. So, we can write down this function in like this, and K is the gain factor of the transfer function. Now, for this function, if s equal to z1, so what will happen? Or s equal to z2 or z3, then the value of the transfer function becomes 0. And these z1, z2, z3 are roots of the numerator polynomial. And for these roots, the numerator polynomial, the transfer function becomes 0. So these roots are called the zeros of the transfer function. Now consider if the s becomes p1 or p2 or p3. So for these values of the transfer functions become infinite. So the roots of the denominator are called the poles of the functions. Now let us consider that when it approaches to infinite, all as the roots are all finite number, so they can be ignored compared to the infinite. So we can say g of s equal to k into s to the power n minus m, and when s tends to infinite, then the numerator is greater than m and the function will have also value of infinite. That means the transfer function has poles at infinite s and multiplicity of order of such pole is n minus m. Again, when s tends to infinite and n is less than m, then the transfer function will have the value of 0. That means the transfer function has zeros at infinite s and the order of such zeros is m minus m. Next is the mathematical modeling of electrical system. So to find out the mathematical modeling, we have to find out here for this example the transfer function of the model. So to find out the transfer function of the model, first we need to write the mathematical model of the system based on the fundamental principle that results in a set of differential equations that relates the input and output. And then we need to find out the Laplace transform of the differential equations by assuming all the initial conditions are 0, because the transfer function, from the definition of transfer function, we can say that transfer function is the ratio of output to the input in Laplace domain by assuming all the initial conditions are 0. And finally, we need to find out the ratio of Laplace transform of output to the Laplace transform of input. So here an electrical circuit is given and we need to find out the transfer function of this system. So we can assume that this inductor as the Z1 is the impedance and that is the LS, because in S domain when we are transforming from time domain to S domain, so for the inductor it becomes LS and for the inductor it becomes 1 by CS. So Z1 represents only the inductor, so it is LS, and Z2, that is the parallel combination of this R and C, which gives us R parallel 1 by CS, and it gives R by 1 plus RCS. So next we need to apply the KVL. So when we are applying KVL, so this VI is equal to, if we are thinking that I current is flowing through the circuit, then IS into this Z1S plus the combination of this R and C in parallel, that is Z2. So IS into Z1 plus Z2. Similarly, the V0S is taken as the R and C combination. So V0S equal to IS into Z2. Now this is equal to Z2 is R by 1 plus RCS. So next we need to find out the output by input ratio in Laplace domain assuming initial 0 conditions. So assuming initial 0 conditions, we are putting the values of V0 and V1. So it gives us 1 by 1 plus L by R into S plus S square into LC. So here also the highest order is 2, that means this is a second order system, and the transfer function of the given system is Js equal to 1 by 1 plus L by R into S plus LC into S square. So let us take another example. Here R and C are in parallel combination and R2 is in series combination. So here we are considering that this is Z2 equal to R2 and Z1 is the combination of R1 and C1 in parallel. So Z1 becomes R1 by 1 plus R1 CS, whereas the Z2 is the R2. So if we apply the KVL in the first loop, then VI, that is equal to this impedance Z1 into IS plus Z2 into IS, or it can be written as IS into Z1 plus Z2. Similarly, for the output equation, we will consider this Z2 only, because this voltage is taken at the end of this Z2. So V0 becomes IS into Z2. Now Z2 is actually the R2, so R2 into IS. So next we know that the transfer function is the ratio of Laplace of output by Laplace of input, that is V0S divided by VIS. So next, putting the values of V0S and VIS, we are getting the transfer function equal to R2 into 1 plus R1 C1S by R1 plus R2 plus R1 R2 into C1S. So this is the transfer function of the system, and in this way we can find out the mathematical model of any electrical system. So in this video we have discussed the mathematical model, which consists a collection of equations describing the behavior of the system and the approach of modeling, the classification of the mathematical models or the systems, the transfer function model, and the input-output representation of the system, the concepts of poles and zeros of the system. And in the next coming video, we are going to discuss on the mathematical modeling of the mechanical systems and the analogy between the electrical system and the mathematical model of the mechanical systems. These are my references. Thank you. Hope After this video lecture, you have a clear idea about today's topic. Now, we will go through some questions answer session in the context of this video lecture. Now, you are requested to go through gradually and try to solve the MCQ questions by your own. Answers are also attached at the end of each question.